Thank you. I would say that it's more. I would insist on a two-sided test. I'm really using this as an example, so that in this case, remember, we're doing this for our own purposes here, and I just want to show you how the differences are between how these things are formatted. But I agree with you that they really should stick to two-sided tests, just because everybody else does, and just because they're anxious to prove that this drug works, that they may not have a good enough argument to you doing for doing a one-sided test. But let's use a two-sided test anyway, just for our purposes. Okay, so now we got to actually have to calculate what z is going to be equal to. Remember z, because I'm not even going to bother looking at t, because we know that sample sizes have to be such. And in both cases, 64 out of 200, 92 out of 64 out of 200 leaves 100 and whatever. 92 leaves 100 and whatever. So we know that in both cases we have more than a sample size of 30, more than 15 on either side of the proportion. So z is going to be equal to p drug minus, or the other direction, p placebo, right? The difference between these two over the standard error. How many standard deviations apart? What's our z-score for the difference between these two? Okay, well, now we got a little bit of a conundrum, don't we? Okay, we have two values here. We have this group and we have this group. Okay, so we need to find a standard error that combines the two of them. And you can go into your various materials and so on and so forth, including the PowerPoints, and you'll find the formula for this. If I get it right, let's see. I think standard error is going to be equal to the square root of P drug minus, I'm gonna make it more general. P1 minus P2 time P1 let's see. No, you know what? I remember. We need a pooled. We need a single in order to do a standard error. We need a single. Again, a little bit of. I've been doing this for so many semesters. You think my memory would be a little bit better. We need to have a pooled standard deviation. We need to have a pooled proportion. In other words, we need to weight these two proportions so that we understand what the distribution is, and we're going to pool these two proportions. So we're going to come up with a new value, p cap, I'm going to call it, and we're going to say that that's equal to let's see the number of people in group 1 plus the number of people in group 2 over sample size of 1 and sample size of 2. Right? See, it's kind of a weighted average of the two of these things. And the number of people in group 1, what's that going to be equal to? That's 64. And group 2 is 92. So that's going to be equal to 156, I think, if I'm right, over the number of people between these two groups, which is 400. Okay, and 156 divided by 400 is 0.39. We're going to use a weighted proportion of 0.39. Okay, and I don't want that to go down there. I want to keep it together. And now I'm going to use that to calculate my standard error. So it's first this. I have two formulas I'm going on here. First, this p cap, which is a kind of weighted average of the two proportions. And now I'm also now going to find my standard error, and the formula I'm going to use for standard error is going to be equal to the square root of p cap times 1 minus p cap times the square root of 1 over n plus 1 over n2. 1 over n1 plus 1 over n2. Pretty nasty, right? Personally, I think there's a lot better chance you're going to get a, this is a good argument for using SPSS, isn't it? Oh, actually, we're dealing with proportions. A little bit more difficult to use it for proportion. But this is an interesting problem in that the calculators get a little bit more complicated than we did before. And once we get into certain kinds of situations where we're dealing with two different proportions, or two different sample proportions, or two different numerical proportions, we have to then re-examine. It's not as simple as when we do a one sample test. We have to examine how we're going to calculate. Usually it's pretty easy to figure out what the top part of this formula for Z is, because you're looking at the difference in two proportions or the difference in two means. But you start to have to make some judgments. If you look back at the PowerPoints, you'll see that there are proportions. There are formulas for standard error for proportions, like this. This is one of the formulas. You'll see another formula for numerical variables, but that'll be broken down into several formulas. It'll be broken down into formulas for when the standard deviations are assumed to be equal, homeoscedastic, or when the standard deviations are assumed to be unequal. Again, another thing that SPSS does a lot more easily for us. One of those fairly simple way to calculate standard error. The other one gets very complicated, okay, because it involves degrees of freedom that are difficult to calculate. Okay, and I'm just going to talk about that very briefly. Okay, so now let's take a look at this, at solving, how we would go about solving this now. So now, if we looked at our total formula, let me see if I can't find this formula around here somewhere. Let me see. Formula, t-test, proportions. I should have pulled this up, I guess, originally. Here, what's this? Nope. Well, that's our formula for our overall p-value, or pooled p-values. Here we go. I think this is it. There we go. Z is equal to the difference in the two proportions divided by the square root of p cap, the one we just calculated, times 1 minus p cap, times the square root of 1 over each sample size. Okay, a little bit of a complicated formula. I'm going to try and do this relatively quickly using Excel. Okay, hopefully I'll be able to get through it pretty quickly, because I really want to get a result on this. I'm going to spin this up over here. So what do we got here? We got P1, and we got P2. Let's call that P drug and P placebo. This is 0.32. This is 0.46. Okay, let's see, our N1 is 200. N2 is 200. Okay, and I want to calculate P cap now. What's P cap? P cap was equal to 0.39. We just calculated that, 0.39. Okay, so now I'm going to go to my formula here. Okay, and my formula is Z is equal to, and I'm going to do the top part first. Z is equal to this one minus this one. I'm taking the liberty of turning them around so I can get a positive number. Okay, it doesn't matter whether you get a positive or a negative Z-score. You're still measuring it against the absolute value of the Z-score anyway. Okay, okay, so that's the top part of the equation. Now I want to do the bottom part of the equation. Okay, that gets a little complicated here, so I'm going to do that in two parts. Okay, I'm gonna first do this is my P drug minus P placebo. Okay, now I'm going to do the top part, square root. Okay, and that's going to be equal to, the square, let me see here, the square root of P cap, which was this, times 1 minus P cap. I'm not paying attention to the questions right now because I'm trying to concentrate on this and get it right. And I think that's all I need for the top part. And make sure I got parentheses in the right places. Okay, so I got this one portion right here, right? So now I'm going to do this other portion. This is equal to the square root of 1 over 200 plus 1 over 200. Okay, and what is that equal to? Do I got that right? I mean, is this going to work out right? It's going to do this first, it's going to do this first, combine them, and then do the square root. That comes out to, actually, it's probably more. It's probably more decimal places than that. Maybe not. That could be exactly right. No, doesn't show it up there. Okay, I'm going to stick with that. Okay, so now our denominator, the bottom part, is going to be equal to, it's going to be equal to this times this. In other words, square root of p cap times 1 minus p cap times the square root of 1 over n1 times n1, 2. It's going to be equal to this times this. Okay, so finally now I can calculate my z-score. And my z-score is going to be equal to the difference between the two portions divided by the standard error.